So, as promised, I implemented the car tracking. This is just a repeat of a slide you've seen many times before. It's the same setup. The only thing that's different, and you'll see why I did this in just a minute, is that I implemented this for kind of a slow car and a fast car. So there's one going at the very slow rate, and there's one that's going more quickly on average around the track. So we'll look at two different rates. And before I show this to you, because none of you have seen this before, do any of you have a prediction of what you're going to see?
If it's faster, it seems like it'd be easier to track because it knows it can rely, not that it can rely on the model more, but that the model, assuming, yeah, it can rely on the model more because you just have additive noise, the same variance.
You can rely on the model more. What do you mean the model?
So you think of the state values, right? You can kind of think of them as being some additive noise to the states, right? So there's some signal to noise ratio in terms of the states versus the noise. And so you increase the signal to noise ratio of the states.
So you're kind of talking about these two components versus that component.
Yeah.
Yeah. Okay.
I can see that. Yeah.
Do you guys have other thoughts about this? What do you predict? It's the 18th lecture.
I agree with Andy because kind of when it's in two different parts of the circle, there's an ambiguity as to whether.
Yeah, like when this is when that touches hits a tangent.
Yeah.
There's a tangent of the circle. Whether the car goes backwards or forwards, you can't.
It gets buried in the noise.
You can't tell from that bearing angle alone.
It depends on how fast though, because relative to the kind of the radius of the track, or how quickly it gets to those ambiguities. Because if it goes too fast, then when it goes around, you're creating more uncertainty because it can jump from basically one side of the circle to the other side of the circle. If it was really going fast.
Well, it's only 2 or 4 degrees per sample, so it's not going from one sample there to one sample over here.
Yeah.
And you can't tell, did it go forward or did it go backward all the way over to the other sort of tangent point?
Yeah, I forgot how we're defining this.
It's a pretty slow car.
If it was 4 radians per sample, that'd be different.
Yeah, that would be quite different. Okay, well. So in this top plot, it shows the measurements, and the true measurements with the noise are shown in blue, and the predicted measurements are shown in green. And I didn't plot the innovations that I advised all of you to do, but if you took the difference between those two, you would see something that looked a lot like white noise. It would look like it was tracking pretty well based on the innovations, if that's all you had. And the true state, I'm initializing the random number generator. I'm seeding it so that we get kind of the same trajectory again and again. And the true state goes up and does this, and the UKF comes up and then it goes down, has the car going backward for its estimate, and then has it come up towards the end. That's what it did. And that wouldn't bother me because this is only a partial picture. I'm not showing how much uncertainty the UKF has in its state. I haven't yet shown you confidence intervals or standard deviation or anything, but there's the error covariance, and from that we can calculate a standard deviation for the estimate of the state, or even a confidence interval if we want to wave the central limit theorem flag and assume that the state estimate is Gaussian. So then there's a question about, well, maybe there's a really wide confidence interval that covers the true state, or maybe it's really narrow and it's just completely screwed up, and you can't tell from this.
What's the scale on the y-axis there? Is it degrees?
I don't remember. Sorry.
Okay.
I don't think so.
Those radians.
This probably is okay.
This is in units of
Lab?
laps, yeah.
Okay.
So we're looking at units of laps here. I don't know what I had for units on the previous slide, and it looks like I may have changed it because it seems to have changed, but I did try to scale so it was units of laps. So, it starts off kind of the starting line is partway around the track, and that's what it looks like. And this is the true state, and this is numerical integration, is how I calculated the marginal. This is not from the UKF. And you would know that immediately, being a students of this class, because it's bimodal. And the UKF is, only tracking the mean and the covariance. And so if you were to plot an estimate of the marginal posterior, you would use a Gaussian PDF to generate, which of course would only be unimodal at any given time. So again, the UKF went down, had the car go backwards. The true car sort of drifted up, and the optimal tracker kind of went up, got a little bit puzzled. This is the mean, not a median or the mode. Got a little puzzled because there was a split here. This was one of those bifurcation points, and finally figured out that the car went up, and the mean went up and tracked, and split the two modes that were here, and then but more or less continued to track pretty well. But the UKF didn't. However, the UKF isn't doing as bad as it at first seems, because if you look at this closely, you'll see that the UKF kind of is off by 1 right around here somewhere, and it starts tracking again. This bump up is the UKF is going up, and then it's actually tracking where the real mean is quite accurately. All the way through, it kind of comes up, and there's 2 bumps, and the UKF does the same thing, but it's off by 1 lap. It's exactly 1 lap behind, roughly halfway through the recording. Here it's got the car going backwards, but then it figures out, it changes direction, and has it more or less, it goes backward a little bit, but then it has it going up and going in the right direction again. But it's a lap behind, is what happened there. So, and again, what I'm showing you here, this is computed by numerical integration. It's optimal tracking. You can't beat it. It's the best in the Bayesian sense. And here's what you get for the marginal posterior estimated by the UKF. Any guesses before I put this up? Is it going to be really big and cover both these with a lot of uncertainty, or is the UKF going to have a lot of certainty and think that the state's actually down here somewhere and it's going to be tight? Is it going to be tight or wide?
It'll be tight.
Thank you for, you're right. That's the marginal posterior estimated by the UKF, and it's obviously it's wrong. I was really happy when I saw this, even though I've been telling all of you the UKF is great. I use it a lot in my own research. And the main reason that I was happy when I saw this is that there's an awful lot of engineers out there using the UKF or the EKF, and they see it track like this, and they say, oh yeah, it lost track, but whatever, you can't do any better. It's it's off by a lap, and it does pretty well out here. But they'll be sort of blissfully unaware that the marginal posterior at certain points in time is multimodal. And if you were using a particle filter, or if you could do numerical integration, or the Viterbi, or some other technique that can account for those cases where you've got multimodal posteriors, you stand a much better chance of tracking well, and also not fooling yourself. I mean, the thing that's most disconcerting to me is not that the state estimate is off, but that it gives such tight confidence. It's so confident, even though it's wrong. It gives you a pretty tight confidence. The car is definitely, somewhere around here when, again, it's got it going backwards compared to where the car actually was.
Very precise, not very accurate.
Pardon?
Very precise, not very accurate.
Yeah, very good. Well, or you could say very confident. But yeah, that's the right idea. There was another sort of split up here, I think, if I remember correctly. I can't go back without screwing up the recording. And it does increase the uncertainty. It does get a little bit wider to account for that. So it doesn't always just lock on to a single mode. Sometimes it does spread it out and says, I've got less confidence, a wider confidence interval. But boy, in here, it's really tight. It's certain. It never detected that the car might have actually been going forward. It was never able to recover. Just once it started going backwards, it kept going backwards, and was quite happy about it.
It seems to remain pretty confident at the first, the first split there, which was a pretty major split actually.
In here, yeah.
Right, yeah.
Yeah, well, it was unusual, and again, when we looked at the innovations, it looked quite good. It's the only way I think you can catch this is if you've got particles or bins in an integral, where you're really looking at what's happening in all the possible places of the state space. I mean, otherwise, it says, well, the measurement tells me the next measurement is here, and that's consistent with it continuing to go down because there's no way it can make that big jump. So I was happy to see that. The other thing is, and I regret that I didn't include this as an explicit plot, but again, you couldn't actually detect it from the innovation. So
Yeah.
you can only rely on those innovations so much. They're your best tool, but they're not perfect. It's possible in a case like this where the innovations don't clue you in that something's gone wrong.
Also, I think this is just one realization, and I don't know how likely it is that in some cases the particle filter would end up being one lap offset, because if you have one lap offset, there's no way to correct that, right?
Yeah. Well, it turns out because I was puzzled by what the Viterbi algorithm did, I actually spent a lot of time really hitting on this, and it's pretty easy to tweak the model, so there's a whole bunch of different modes that it could pick, and I've been able to see both what the optimal tracker and what the particle filters pick when there's a whole bunch of modes, not just occasionally a split of two, but where there's it could be any of a large number. You can increase the process noise or increase, I forget how I did it exactly. I think I increased the process noise, but when you do that, you're absolutely right. One mode will usually dominate, and it will kind of lock onto one mode. Again, depending on what you're using to track the estimated posterior. But it can be off by a lap as well. All the trackers are susceptible to that. It's not just the UKF that is susceptible to picking the wrong mode. The others can also. And when I say wrong, I'm really comparing it to where the true state is. Another way of looking at that is for your measurements, it could be very ambiguous that for your measurements, it may be just as possible that the true trajectory is in one mode as it is in another. So there's an ambiguity there as well. Okay, but I did also speed it up. This is with a slow car, where it could be kind of going backwards a lot. It's improbable, but it's also improbable that the car went so much faster than the average rate as it actually did there at the beginning. So this was a case where it's what's going on? It's not consistent with the process model, and the measurements are telling you something else. So it was a tricky case, but I like that about it. It's less tricky when you speed things up, because then you've got that prior knowledge about the car going pretty fast, which makes it less probable that the car would go backwards around the track for a full half lap, or a full, I think it was only a half lap. So, or I should say from one tangent point to the other tangent point, it could actually be more than 180 degrees. But in any case, this is it tracking with a faster car, where prior knowledge in some respects is better, whether you think of it in terms of signal to noise, the way Andy described, or you just think of it as the car, we know its average rate is faster, so it's less probable we'll go backwards. There's fewer modes now that split out as we go. So this is, again, I'm sorry I didn't plot the difference, but this is the predicted and the true. And clearly I've done something funny with the scaling here. I must have tried to convert it to degrees or something, but I think I did it wrong because the state is in units of laps now. But now you can see that the true state and UKF estimate right on top of one another, tracking really well. That's got it. And here's what the true posterior looks like, the true marginal posterior. Again, this is calculated with numerical integration, so it's not from the UKF. And there's still points where there's sort of very small other modes, barely. They're just barely there. They're pretty faint. Again, because we've got the prior knowledge that car is zipping around faster, so it's sort of transitioned from being multimodal at times to really being essentially unimodal almost all the time. And so you see all three estimates are quite good, or I should say the two estimates, the blue and the green, and then we've got the red underneath. And that's where the true was. And it's always going to be noisier.
I'm having a hard time convincing myself that increasing the angular speed will reduce, say, a performance metric like, if you measured RMS error, something like that. Why I don't see that? I mean, I can see why in this example it was able to correct how many laps it covered.
Yeah.
But I think that's also because we are so if you look at the first graph with the 2 dB per sample plot, so the noise was in a positive speed direction, so like it covered 300 degrees in 30 seconds instead of 60 degrees of average, right? And now we are making true closer to that because we are using the same seed, right? So it's kind of like, okay, it's making tracking easier for that particular example. I see that. But I don't see, like if you took the speed to be minus 4 degrees per sample, I think it will have a harder time to track that because the noise will be, and keep the noise the same. I think that will be more difficult to track because noise will be in opposite of the true state.
I was with you until that very last bit. I don't think the direction of the speed makes any difference at all.
Just for this realization, I think, because the noise will be such that it will go opposite to where your model says it should.
Oh, yeah, I see what you mean. Well, and this one is different. This was seeded with a different random number generator. But in the previous example, where there was that jump up because the process noise was driving it up unusually high by a lot. So then it would track better. I certainly agree with that without having tried it. I think you're right about that. And I would have to think through the main point that you're making is that when there is just a single mode, maybe it tracks just as well in these regions where it's not ambiguous. Maybe it would track just as well regardless of whether it's going around at 2 degrees per sample or 4 degrees at a sample. The main point that I don't think you're disputing at all that I was trying to explain is the weakness of using the Kalman filter when your posterior becomes multimodal.
I take it you didn't increase the magnitude of the noise for this. That's
Correct.
why the mode went away.
Say it
So
again?
you could get the exact same effect. If this was double the velocity, you get the same effect by having the noise and keeping the velocity whatever it was before.
Not quite, because the ratio of your measurement noise, your process noise will change then too.
Yeah, well, there's the 3 components that go into the model because it's a random walk. So I'd have to think it through because you've got the state of time n plus 1 is equal to what the state was, plus the angular rate times, well, it's per sample in this case, so just plus the angular rate plus the noise. So there's all 3 components.
It would be exactly the same, but it would be closer to single mode in that case with less noise.
Yeah, I think you're right. That would be equivalent. Yeah.
Yeah, and if the tracking accuracy does depend on speed, that'll be interesting because there'll be like an optimal speed, like at some degrees per sample, you'll track it the best. Faster than that, it'll decrease performance. Lower than that, that's what seems kind of strange.
That does seem kind of strange.
And it makes
But
sense
keep in
with
mind,
the-
this is constant velocity.
Right.
So I think as you increase you could eventually get to the point where it's making
Yeah.
a whole revolution. So that would make it worse. Yeah, there would be a sweet spot in that case. I mean, these things happen even with fairly simple nonlinearities as we have in this example. It's only a nonlinearity in the measurement model. So yeah, that is interesting. I hadn't thought about that when you really take this up to the limit, what's going to happen. But yeah, that's a good point. Yeah, you're right. So one more example in the car tracking. When I move forward and I show you now what the estimated marginal posterior looks like for the UKF, what do you think it's going to look like? Especially in a period like this where there's a little bit of stuff up there or there's a little bit of stuff down here. You guys ready? Because I can't go backward. I can only go forward, side by side. So watch carefully. It's going to turn yellow.
Ah, very similar.
It loses some of those very small bits that were out here. It's unimodal. It has to be. It's just a Gaussian with a changing variance. And the variance is bigger when it was a little bit wider, but it's just tracking a single mode, and it kind of ignores those little bits that are out there.
It's really almost invisible.
What's invisible? Oh, you can't see the yellow. Well, thank you, Scott. Sorry. Hardly any better. You can kind of imagine it though because you can barely make out the edge there. I wonder if that's an optical illusion or if that's a projector. I wonder if that's our eyes that create that little bit of yellow there on the screen, and then it sort of fades down here. And our eyes do things like that. Oh, really? You can't see that?
No.
Do you see a yellow fringe there?
Yeah,
Tinge?
well, we'll just have to go to the video and see.
Yeah, theory lateness.
On my screen, it's all yellow and does it differently. Interesting. Okay, you can turn the lights back on, Scott. So that's what it does for the car tracking example. If your posterior is unimodal, UKF does really well, even in the nonlinear case. If it's multimodal, you may be deceived and you could be completely oblivious to that and just not know it. So be careful. That's one of the central messages of this class. I do have one other example I wanted to show you. So in this case, I'm changing the measurement model, where now the measurement model is linear. So I just say, let's say we measure the phase angle directly somehow. So now, this is bearing angle. Let's say, and I think I said, suppose this is a camera that's pointing at the car and it's tracking it, and you're just measuring what it is relative to some kind of fixed reference. So this would be equivalent to putting the camera in the middle of the track. So it's measuring the phase angle directly now that we're trying to track. So now the thing's linear, right? We've got, it's not even a random walk, it's increasing. It'll go over some number of cycles. And I'm going to show you, as before, the same three plots. But I want to ask for a prediction. When we look at optimal, what's that marginal posterior going to look like now?
It's going to be Gaussian, right? Because it's the optimal for linear system is the same as the common filter, which is Gaussian.
Yeah, exactly. Yeah, you could apply the common filter to this. Exactly, yeah. And what's the UKF going to do?
It's going to do the same thing.
Okay, Andy's got a prediction. Let's see if it's right. So once again, these are the measurements on a terrible scale. I apologize for that. And the predicted measurements. Things would look white if I plotted the difference. The true state went up here. The UKF estimate went down here.
It's a lag.
It looks like it, although if you look carefully over here, I'm sorry that I put the label there, but it catches back up over there. Okay, so on this example, I actually had to increase the size of the green dots because I wanted to see it, and it was covered by the blue dots. Can you guys even make that out of the projector where you see these blue dots have a shine around them? That's because they're directly on top of the green dots. And yeah, sure enough, this was calculated numerically. This is the same thing that was capturing all those multimodal cases. But now, even though we're computing it numerically, it's Gaussian. As it has to be. When the linear case, Gaussian noise, there's no nonlinearities. It has to be linear. And the true state was up here, but that was unusual even for those measurements that just kind of happened in that particular realization. And I think that the 95% confidence interval only covered the true state about 90% of the time, but it's a pretty short realization. And of course, if you did it across ensemble, it would be exactly 95%. And again, we see the growing uncertainty just due to the level of noise. And if you look at this carefully, you'll see over at this right edge that the blue dots kind of deviate a little bit from the green dots. Does anyone know what's going on there? In that case, it's not the green dots are off, it's the blue dots. The numerical integration got screwed up at the end. And it's because it got clipped a little bit by being too close to that upper edge. And that's what caused the blue to go down a little bit. It's because I didn't set the upper limit of doing the numerical integration high enough. It's just a numerical integration error. Otherwise, it would have continued to be exactly right on top of it. And so when I go forward to the final slide here, where I show the marginal posterior estimated by the UKF, fitting a Gaussian based on estimated error covariance, what's going to look like? If you could see yellow. It'll look the same. The only difference is going to be out here in the confidence intervals. And again, it's due to the numerical integration being a little bit off. So here I'll go forward. Same. And that's really cool because we had this very powerful general technique, the numerical integration, unidimensional case, but the UKF does exactly the same thing, way, way, way more efficiently. So as it should, So UKF works really, really well for a lot of nonlinear models as long as the posterior is unimodal. And to figure it out, we had that discussion. It's not trivial to figure it out. But you're going to want to put the time in to try. And we'll see some examples as we go through the case studies. And those were the only new slides that I added. I don't have anything else to add for this lecture. This is the same summary we went over before, but I did circle back and finally, well, granted your request of looking at the card tracking example. So any last questions on the UKF? No? All right.